So good morning. Today we will go on to a topic in detail about undecidable or non-computational problems. Undecidable problems, they are even called as non-computational problems. Now, they are called non-computational because you do not have a generalized algorithm for such problems. You have a procedure, you know how to do it, but calculating the time and the space, it is not possible. So such problems are called non-computational problems. There are several non-computational problems, out of which I've listed out a few. We have a problem called the halting problem, post-correspondence problem. We have a problem called Wang tiles. It's very interesting, where you can arrange tiles in a specific pattern. Then there is a game called Magic, the Gathering, and much more. Now we will be learning in detail about the halting problem and the post-correspondence problem. So let us first look into what do you mean by a halting problem. Now, before we go into halting problem, you should learn what do you mean by halting. Halting in very simple terms, it is stop, terminate. Okay. Now, halting in a program means that when you give some output, some input, when you give an input to a program, the program will accept the input and then terminate or halt. That is one possibility. The input is accepted and the program stops. Another possibility is the input is rejected and then also the program can halt. The third possibility is it can go into an infinite loop. Okay. Now, in halting problem, what we concentrate is you give an input, the machine should accept it or reject it and then halt. And you must even make sure that the machine would never go into an infinite loop. Now, this halting problem, it is actually not a problem. It asks a particular question to you. Given a program, will it halt? Or in other words, to be very simple, it is something like this. Is it possible to tell whether a given machine will halt for some given input? Now, if you look into the block diagram, you might understand it much more easier. You given an input string into a machine. Let's call the machine as a halting machine, a machine which will either make you halt or go into an infinite loop. Okay, so the output would either be a yes or a no. If the output is a yes, it means that the halting machine halts. If the output is no, it means that the halting machine does not halt. Now, be it whichever undecidable or non-computational problem, they should be, as I told you in the earlier class, they should be giving you an answer of either a yes or a no. Okay, so be it whichever undecidable problem, you should either be getting an answer called yes or an answer called no. Now, the concept in which you should either be getting a yes answer or the no answer, you call it the Einstein problem. It is called the Einstein problem. It was coined by a computer scientist called Leibniz. Leibniz came up with a problem called Einstein problem, where it means you should either be giving an answer called yes or an answer called no. So halting machine also, it follows the same problem, which tells the machine should either halt or the machine should not halt. Now, let's talk in very, very simple terms. You might be writing programs in n number of languages. Let's say C, C++, Java. You might be writing programs. Now, what this halting problem means is, how can you know whether your program will go into an infinite loop or not? Or in other words, can you design an algorithm? Okay, can you design a generalized algorithm for which the input will be your program? You give in your program as the input to the algorithm. The algorithm should give you a yes or no answer telling whether your program will halt or not. Okay, you get an answer, it is halt. You don't get an answer, it will not halt, which means, it would go into an infinite loop. Now, you might be thinking, okay, I have a program. Can't I find out whether it goes into an infinite loop or not? Yes, you can actually find out. The only way to find out whether a program goes into an infinite loop or not is you should run the program. You should be running the program. You should manually run the program or execute the program and then find out whether the program you can be able to obviously find out whether the program goes into an infinite loop or not. Okay, you can run the program manually and then you can find out whether the program goes into an infinite loop or not. But what we want over here is, can you design an algorithm? Can you design an algorithm where you give in your, imagine you have 2000 programs, okay? Into this algorithm, you give these 2000 programs in. Can you tell whether the algorithm will tell you whether the program will halt or not halt? Not halt means, go into an infinite loop. So that is what the halting problem, okay? So now what we are trying to do is we are trying to prove the undecidability of the halting problem. Now, this halting problem, it is proved by contradiction. Proof by contradiction. So, we tried telling that you cannot have such a machine. Okay, you cannot have such a machine, or you cannot design such a generalized algorithm which tells whether your program might halt or go into an infinite loop. So because we are doing proof by contradiction, let us assume the reverse. Let us assume that we can design a machine called H, okay, a machine or an algorithm, whatever. Okay, so say that you can design a machine called H in which I take in two inputs. One is an input called P. Okay, I'll just write over here where, so P is nothing but my program. P is the program and I is the input. Okay, so I have a machine called H, which will take in two inputs. One is P and the other input is I. So, let me just define my, okay, so I have P and I. So let me write a simple code for that. Now, what will this HPI do? Okay, two things which can be done. One, it can halt, and the other one, it is not halt. Okay, these are the two things which this particular machine H can do. Machine or my generalized algorithm can do. It can either halt. What can halt? P will halt. P will halt on an input I. Okay, P will halt on an input I. That is one possibility. The other possibility is P will not halt, or P will go into an infinite loop. P will not halt, or it will go into an infinite loop. So these are the two possibilities of my machine called H. It can either halt or it cannot halt. So now let me just write a small code for this. Okay. Okay, before writing the code, so that is my machine called H. Now, similarly, let me assume I do have another machine called C. Okay, C is another machine, or C is another algorithm where, X is a program, X is a program. Okay, X is any program. X is a program. Now let me write the code for C. Okay, now here we already know the code is this. It can either halt or it cannot halt. Now let me assume write the code for C. Okay, now just like H, C will only have two possibilities. It can either be halt or not halt. Now I write if. Okay, see, look here. This has only one input, this has two inputs. So it means that, C is a machine which will take in the program as the input, where, X is the program and X is also the input. Okay, X is the program and X is also the input. So I write over here, if X comma X. Okay. The program in consideration is X, and even the input which I am passing is X. That is why I wrote over here simply CX. Okay, if HXX is equal to halt. Okay, like, if my machine is equal to halt, do something else, do something else. Okay, now I'll just simply write a code. I can write however the code I want because then I'm designing my own algorithm. Let's say if it is halt, I'll come back to this later. Okay, I'll come back to this while arrow loop forever over here. So I'm simply writing my own code. I'm writing my own code for CFX. If HXX is equal to halt, loop forever. Else what do I do? Else let me say, else return. Else return. Okay, if it is equal to halt, loop forever, else return. Now return means, it will terminate or it will halt. Okay, loop forever means, it will go on into an infinite loop. I have no control over it. Okay, so I have designed another machine or another generalized algorithm called CFX, which tells me if HXX is equal to halt, loop forever, else return. Okay, now let's run C on itself. If we run C on itself, okay, if we run C on itself, like, you'll be running it like this, C on C. Okay, imagine you're running the C machine on itself. The input is also C. You will have two possibilities. One is H C comma C is equal to halt. Okay, the first part is C comma C is equal to halt. And this one is the else part. The else part is actually what? H C comma C not equal to halt. Not equal to halt. Okay, so let's take into consideration step by step. Okay, the first possibility, after which we will look into the second possibility. Now, as per my first code, I'm writing HXX is equal to halt, which means loop forever. Loop forever means it is not halt. Okay, you're going on looping. It is an infinite loop, which means, you are not going to halt. Okay, now we'll look into the else part. Else part means what? Else part means return. Return means you're returning something at the end of the day, it will halt. Okay, now look here, you have come into a contradiction. Okay, you are telling if it is equal to halt, then it is not halt. And if it is not equal to halt, you are telling the machine to halt. Okay, so look into both of these. This is actually a contradiction. It is illogical. You are trying to tell if it is equal to halt, go for not halt. And if it is not equal to halt, then you better halt. Okay, so very simple. So the machine does not exist. Okay, or I'll just go simpler terms, which means the assumption is false. Okay, so what was the assumption? We can design such a machine called H. That was your assumption. So we cannot design such, thus we cannot design such a machine. So the halting problem, it cannot be solved. You cannot design a machine which will tell whether you can decide whether a program will halt or not halt. Now, the doubt which comes into all of your minds, I'll clarify that. Okay, I'll come over here. Okay, you might be wondering, okay, if you write return over here, okay, imagine you write return over here, and then you write loop forever over here, this will reverse. It will be, okay, equal to halt, halt, equal to not halt, not halt. Okay, imagine you reversed your code a bit. You will of course get another result. But the proof of contradiction, it tells that, okay, the proof of contradiction, it tells that for any one example, for any one logic or any one line of code, if you are able to prove a contradiction, it is a contradiction. Okay, so I tried to write my code in the reverse, which proved that to be a contradiction. So very simple, this is a contradiction. Okay, so I go again. In contradiction, we just need one simple example to prove the contradiction. If with the help of one example, you are able to prove a contradiction, the whole thing is a contradiction.